Hello, everyone, and thank you for attending this session called Inside the Black Box Generative AI Technical Deep Dive. This is ServiceNow Community Week, and I'm very happy to be able to present to you this session, which was first presented at Knowledge 25. So my name is Anders Figenschow. I work at KPMG, and so I've spent a long time trying to figure out how AI actually works. So we all know sort of what we can use generative AI for. You can make images or music, you can generate text, or now that AI agents is a part of the platform, that's what we're most excited about. But I think that in order to really be able to utilize these wonderful tools, I think it's important to understand how it really works. So that's what I've been trying to do for a while now. So let's just start. Have some slides, and I'm going to show you some proof of concept, and let's see if we can understand how AI works. So first, a little bit about myself. I am Anders Figenschow. I am a certified master architect and MVP in the ServiceNow community, and I work in Norway as part of the ServiceNow practice at KPMG. And I've been working with ServiceNow for around 11 years now. So topics for today, as you can see on the screen, it says machine learning. It's not too much to say about machine learning. We can go through that really quickly. So the terminology of machine learning is very broad. So if there's something a machine can use to learn something over time, it's usually statistical models based on large amounts of data. You can say that's machine learning. So the difference between machine learning and artificial intelligence, it's a bit hard to find a consensus about. So in my opinion, it's artificial intelligence if it's more than just statistics. So when the statistics move over to actually help you in your daily tasks and do something that people would normally do. That's just my definition of it, really. So we'll move from that one to AI and what is a neural network. We'll talk about what that would look like if you made it from scratch, like I did in ServiceNow. I'll show you how that works. And we'll move over to the large language models, which is the brain of our agents. And you all know ChatGPT, that's a large language model. And in the end, I'll have a brief line of thought about the agentic AI in ServiceNow and where I think we'll be heading from here. So neural networks. So the design of a neural network is, I'm going to use a line of words as an example. So how you would train a network and how you could use it. So first you would take a sentence. Let's say, please reset my password. And this is not a sentence, a random sentence from somewhere. It's basically, my example later will be where a neural network can take like a short description from, let's say, an incident, and we'll use this in the neural network to predict an assignment group. It's sort of my hello world example. So in this case, if you want to train the sentence, please reset my password in the neural network, you'll first use a technique often used in search engines, which is to remove the stop words. The stop word is a list of words that makes no sense or gives no value, right? So if you want to make like a catalog of words or combination of words that would represent an assignment group, including words that is represented throughout the entire corpus, or the words will represent any assignment group, then it makes no sense to keep it there. So in search engine, it's the same thing. So if you search for the word please, you can find any article, right? Or my, or like general words, makes no sense to include in a search. So it's the same thing in neural network training. So you remove the stop words to make it as short as possible. I'm simplifying. In some cases, you want to include these, but then only in a context, and you want to like train the network where all of these are paired together. But that's going a bit further than we have time for. But just to simplify it, we will use stop words. And after we have that, we vectorize it. So a vectorizing this sentence would be to put all the words in a list. You can call it the dictionary, and every word gets its place in the dictionary. And to vectorize it will be to say, let's say all of these blue dots here represents a word, and the red dots are these two words, reset and password, are in these two positions. So if you want to vectorize this, you can represent this with a binary number. So all the blue dots is a 0, and the red ones are ones, right? So 0, 0, 0, 0, 0, 1, and so on. And that way you can have rather short strings that represents a pair of or a range of words, right? And if the length of the dictionary is always the same, so all of the words, like if you take all the unique words in your incident collection, let's say that's 500 unique words, so the vector would be 500 long. And one short description from one incident is a set of ones, the positions of ones in the string. So we're gonna place this up and down now because it's easier to visualize later. So it's the same one, we'll just call this the input layer. So when we have a training situation, you take all the words, remove the stop words, and you vectorize it, and this is your input layer. And you will iterate through these many, many times. But you have more layers. So you have the output layer in the end, and the output layer will represent the assignment group in our example, right? So that's a set range. So let's say you have 25 assignment groups in your instance. That's a list of 25, call them nodes, right? These dots. And what we want is for any input layer vector to be translated to one output layer. They will point to many in the end, but one will be stronger. And just hang with me and I'll show you how that works. The hidden layer is like our calculator. So while we are sending in data through the input layer, we'll send this data to, at first, random points in the hidden layer, and from the hidden layer, random points in the output layer, but we'll give it a score. So how well did it perform during the training? And going back and forth there will give us a trained network that understands the results of these combination of words in the input layer versus the output layer. So pushing the trained data forward is called a feed forward. So you're guessing. So in this situation, let's just say we'll give it a score between 0 and 1, and we'll just give them random numbers. So we'll might as well give it a 1, like a successful estimate. So these two words are going to be placed in a random hidden layer and then a random output layer. But in the training, we know the result. We know that this specific sentence means this assignment group, right? So when we get to the output layer, we can say if it was correct or not. So in this situation, you can say that if you look at this one, it went to a hidden layer here, and it went to this one, and it was like the correct one, or a more correct one than not. So it got a bonus on the pathway back. So we distribute blame or give it a price. So we gave it a price, like added a little modifier on this value. And this one was wrong, so it gets a penalty. So the number gets lower and this one higher and that one, and it goes back. And then you have a modifier in the hidden layer as well. And it's based on some math. I'm not going to go into the specific of it, but basically what you're doing is to adjust the pathways to be stronger or weaker for this combination. So, and you can have many hidden layers. You can have a lot. So for large language models, it's a lot of hidden layers. But for a hello world example like mine, we just need a one layer. So after doing this a lot of times, we test and adjust. You just send the same one back and forth through this feed forward and back propagation until the numbers are sort of landing onto something that it feels is truth. So all of these will be hit through the randomization, and they'll get values for the pathways. So once you do that, you can send in through the input layer something else, something that you didn't train on, but it'll look at the statistical results of the training through a combination of words, and it will follow the strongest pathways and land on a conclusion. So in this case, these two words went to two different nodes in the hidden layer, but the strongest pathways from them went to a specific assignment group, and that's the predicted assignment group. Right. Let's have a look at the demo. So what basically I did was to make one of these models from scratch, right? So I wanted to see if I could make a neural network with JavaScript and not using any engine anywhere, nothing like that. And I wanted to see if this could work, because this is the way I learn things. I make something, and if I make it work, then I understand it better. If I just read a book, it's very hard for me to really understand, and I feel like I'm just repeating a theoretical bunch of knowledge that someone gave to me. And it might be wrong, you should question everything. So if you look at this side here, this is my input layer, and it's a lot of dots, because every dot should represent a word, a unique word in my collection of incidents. So I've trained this on the short descriptions in my incident collection, and these incidents are straight from a demo instance or my developer instance, and from whatever I could get from ServiceNow. So it's out of the box, example incidents. I didn't make anyone myself for this. It gave me some issues, and I'll show you in a second. So, and anyway, so there's too many words. So if I made one dot per word, this would just be one fat line down here. So these represent like 5 words or something, just the visual part. And then you have a hidden layer, like I showed you in my slide, and each of these dots represents an assignment group. And once I start typing, it will immediately try to predict the assignment group. You'll see. So for each word I write, it will very quickly go through this, and you can see how fast it's going, and the different assignment group names will show up here. And the strongest one at any point of time will be shown in this text field here. So I have some examples. Let's do password for SAP account. Password for SAP account. Right, so you can see it immediately, because it doesn't take a long time to check what is the strongest pathway, right? It's showing everything it's trying out, which has a value at all. So some of them have weak ones, because account might be many places. So account is probably mentioned lots of times in incident management, in ServiceNow service system support, but the combination of these words were most likely to be in SAP support, most likely because of the SAP word. So it predicts this. So this is real time, no latency, done directly in the client, because this network isn't that big of a file, so we could just load it and unload. I'll do another one. Let's do error opening page in Oracle, right? The same thing here. So you see these 4 starting points is most likely error opening page and Oracle, and in is most likely just ignored because it's a stop word. So you can find stop words as a table in ServiceNow, and it's being used for the search engines, and you can just reuse this one if you want to make something custom, because it's a good table to start up with, and you can add words if you want. Yeah, let's do another one. Let's do okay, I'll do something funny, because as you know, so many people don't say ServiceNow, they say snow. Let's check out this one. If I do database error in ServiceNow, it's having a hard time finding any results, and everything over here is too weak, and it's basically defaulting to technical services support, so it doesn't find anything really it doesn't know what to go to. But if I say snow here, look how much it's pointing to ServiceNow. Have this in mind when we go on to our next section here. But basically, this is a neural network, how it works, how it looks like. And the point is not to make your own neural network. You don't really need to. but this is just to show you how it trains the network and how it uses it after. Right, let's move on back to the slides here. Right, so yeah, it seems to be imbalanced. If you saw my ServiceNow Snow example, why did ServiceNow show nothing at all while Snow showed the ServiceNow group or predicted the ServiceNow group? The reason is the data sets are imbalanced. So I made a report from my developer instance, and you'll see the same one if you have a developer instance and you just run a report on it. You see that the demo data that ServiceNow provides is very, very imbalanced. So technical services is almost more than half, I would say. If you go down to the ServiceNow system, so the tickets in ServiceNow assignment group is about 200 and something. It's not too much, right? And you would maybe think that maybe that's enough, for this. But if you look at this from the list view, almost all of the ServiceNow, the tickets in ServiceNow group are actually mentioned at Snow. So ServiceNow demo data is saying using Snow and not the word ServiceNow. And if we go to the next page, you can see that the word ServiceNow in the short description is actually just 14 records. So it takes a lot for the neural network to understand that ServiceNow is an important word for this type of group. That's the ServiceNow group. So that is why Snow showed up and ServiceNow didn't. 14 records is too little. So what can we do about that? So there's a few solutions about these data sets that are imbalanced. And that is one thing I think is one of the takeaways of understanding neural networks and AI, is that if your data is imbalanced, the training of the network will be as well, and you might get some weird results. So it's very important to look at the data you're going to train first and make something, do something to make it balanced. So what I mean about balance is that let's go back here. If all of these were lined up nicely, it would be perfect, right? So then it doesn't prefer this one to this one, right? So there's a few ways to do that, and these are some known methods of balancing data sets. Oversampling is that you push lesser data sets up. You should basically repeat them. Undersampling is the opposite. You push something down. And you have some mathematical ways to do it. We're not going to go into the details, but just know that there are methods, and there are reasons why when people say you need to train your AI models, you need a minimum amount of data. So a representative amount, a lot of data. The more data you have, the better. So let's talk about large language models. And attention is all you need. It's actually a white paper called that, which was the basis of these language models that we know today. Right. So in 2017, Google came with this model called the transformer model. And it's a bit too much to look at and understand, but let's go to a simplified version. So there's a simplified version. So Google came with this model that had two parts, an encoder and a decoder. And the first use case for this was the Translate, the Google Translate. So what it did was it trained a lot of sentences and put it in the encoder, and you can match it against a decoded version, which was another language. So you basically wrote something in English, and it knew, because of the training it had and the vectorized data it had, how to properly translate it in decoder sections. You basically sent in some values into the decoder, and it immediately came out. That is why when you're using Google Translate and you type something in and you click translate, you immediately get the entire sentence immediately translated. That is not what a large language model will give you. It will give you, it looks like it's typing, right? If you get a reply from ChatGPT. So that's why in 2018, OpenAI realized that if all the data is in one of these parts, like in the decoder, you don't really need to encode any part. You just need a decoder, and you can do it one token at a time, or to simplify it in an understandable way, one word at a time. And you just predict the next word, and you don't need really to have two models, which makes it twice as big basically. So in this one, you have something called self-attention. So you have the words in your data set, and you record the relationship between them and give them a score. So let's look at this sentence, the cat sat on the mat. In this sentence, if you want to have self-attention in this one, you can say that these two words have more importance to each other in the relationship than maybe two other words, right? These two words have a relationship. So you give, between cat and sat, you give them a value that shows that it has some importance. But also these two, on and mat, it has some importance as well, more than the and on, right? So it makes more sense to give them one as well. So when you train this, the model understands that these words have some relationship or have some more importance due to the statistical findings it has. It sees that these are more likely to be together, and it gives some context. So it gives an indication of context by giving them a value of like attention. One word has an attention to the other one. You can also do this with pairs of words or many words. So you also get structure. So you can have the cat has a relationship to the mat, and they get a value, but also the cat and sat, right? So you keep doing this, and all of the words or tokens get an attention to all of the words in the same sentence. And it's being recorded in these large neural networks, which have many layers of like dimensions in layers. So in my example, we have just like a very simple layer. It's like a 2D layer going from left to right and right to left. But in this case, you can have hundreds of layers. So it's easy to see it as a 3D model. Like you can go many directions in space, but in reality is more than that, right? So it's hard to visualize, but that's how they do it. So there's a vector between these words. All right. So how can these large language models answer questions, right? That's one of the things I wanted to find out. What it does is it really just understands one word, and that's what surprised me. It doesn't understand your question, and it doesn't understand the answer. It understands one word, the next word. So it takes your sentence and predicts the next word in that sentence. So what is the capital of Norway is one example. The next token would be Oslo. So if you look at that one, it takes this, and through the attention layers, it sees that the next one is Oslo, because the combination of these words, if you have self-attention to these, Oslo is the next word. And then it can keep guessing the next, or predicting the next token or the next word. So it says Oslo is the capital of Norway, or it can do a different structure, right? And how can it do a different structure? Well, it doesn't really care about the difference between a prediction of a word and the following word, or how the structure works, right? So a structure is also recorded through these sets of sentences, sets of words with self-attention to other sets of words or sections of words. That's why you can ask ChatGPT to write you a poem, and it'll actually do that. Even though I would say that it doesn't really look like a human wrote those poems. It's not there yet, but one day maybe. So there's no difference between text structure and content for GPT, because the training data has both at the same time. So Agentic AI, so we all seen the AI agents in ServiceNow. So I didn't want to take out a screenshot of that now, because for the last few months it's changed a little bit. So it might change even before this video comes online. But so this is from a different system. But that really does the same thing. So it has some input, maybe a chat message or an email or whatever. And the AI agent starts with the large language model. So what we've been talking about is it'll sort of understand the input and predict what you want to do. So, and by predicting what you want, maybe you saying that I want you to check my email, then it will say, okay, I'll check your email, but it will structure it as a JSON object, and the code behind the agent will understand that that means trigger this and that and do some stuff. And this is basically the same thing that ServiceNow does. So ServiceNow has some user input or it's automated or whatever, but it also triggers a large language model. And you have the Now LLM, but you can also choose the model to be OpenAI or other models as well. But they are there to understand the context of the input. And from there, you are using some tools, which is scripts or flows or search retrieval. You can use some information or data to support your decisions. And it uses Now Assist to output things in the chat or have a follow-up dialogue with the user. Right. So this is basically how the agents work in ServiceNow as well. But I think the most important thing is to understand how the large language model works, because the Agentic AI uses these models as the core functionality. So by understanding the models, you might get better results when you set up these agents. And this is a very important part. It is important to understand that the language model is a prediction model. It's not like a person who understands what you really want. You have to be very precise for it to be able to predict the next token, right? And it is based on statistical data. So when you are making an agent, you have to be very precise in your prompts and not allow the large language model to guess. So the more vague you are in your instructions for the agent, you might get the wrong results. So what is too detailed or vague enough or whatever, that's for another discussion. But I think that is the most important takeaway of this. Now that you understand how the large language model works, and now that you know that Agentic AI is using a large language model to understand the tasks it's doing. So by that, I'll quickly go back so I can say goodbye to you. Thank you for listening and checking out my sessions on Agentic AI. And I hope I'll see you the next knowledge in May 2026. Bye.